Assalamu alaikum. Welcome to my YouTube channel. Today we will be discussing about A-star algorithm, which is a variant of Dijestra's algorithm, which we have discussed before in one of our videos. So, what A-star algorithm does is it is considered one of the best algorithms for searching, for pathfinding, for path planning, and it has quite a lot of applications. A-star search is an informed best first search algorithm that efficiently determines the lowest cost path between any two nodes in a directed weighted graph. So, directed weighted graph with non-negative edge weights. So as you can see that there are a lot of terminologies involved. So if you don't know about graphs or what weighted graphs are or what edges are or what negative edges are, you can see one of my videos in which I introduced graphs first. But in this video, we are going to talk about how to implement this A-star algorithm through an elaborate example. So first, we will try to understand how this algorithm works. And this algorithm works using a simple technique. And this technique follows an evaluation function. What this evaluation function is for A-star search is given by f of x is equal to g of x plus h of x, where g of x is the cost to get to that node x, and h of x is the heuristic that this node that we are going to represents. You will see shortly how this works. Now, how this algorithm is implemented is something like this. The algorithm is implemented in a similar way to Dijestra's algorithm, given a weighted graph with a non-negative edge weights, so emphasis is on this. To find the lowest cost path from start node to the goal node, we have to create two lists. One is called the open list and the other one is called the closed list. An open list, which is obviously implemented as a priority queue, it stores the next nodes to be explored, as we will see shortly. Because this is a priority queue, the most promising candidate node or the one with the lowest value from the evaluation function is always at the top. So in this case, the lowest key or the lowest cost node will always be at the top, and that will be evaluated first. So initially, only the start node will be the part of open list. Now, what is a closed list? It contains, in short, it contains those nodes which we have already explored. Now, to find the lowest cost path, we will build a search tree which is constructed in the following way. The first step is to initialize a tree with the root node being the start node. The second step is to remove the top node from the open list for exploration. The third step is to add the current node to the current closed list. The fourth step is to add all the nodes that have an incoming edge from the current node as child nodes in the tree. Fifth step is to update the lowest cost to reach the child node. And the sixth step is to compute the evaluation function for every child node and add them to the open list. And this process is repeated until we reach the destination node, or this destination node or our goal node is part of our closed list. Don't worry, we will explore this through an elaborate example, and then I will try to explain how this actually works. Now, the lowest cost is updated as the algorithm progresses in the following way. How we find the lowest cost? The current lowest cost is equal to minimum of the current lowest cost or the parent node cost plus edge weight. So we will evaluate these two values and we will find the minimum of these two values, that will be the current lowest cost. All nodes except for the start node start with the lowest cost of infinity, and the start node has an initial lowest cost of 0. The algorithm concludes when the goal node is removed from the open list and explored, indicating that the shortest path has been found. And the shortest path is the path from the start node to that goal node. I hope you get this, uh, but we will see shortly through an example. Now, the important part is that algorithm ends when the goal node has been explored, not when it is added to the open list. It can be part of open list, but when it is added to the open list, the algorithm doesn't end there. The algorithm will end only when it is part of closed list, our goal node. Let's take a look at an example. As you can see, the start node and end node is indicated through red and green colors. So in this elaborate example, we have the starting point S, and our destination point or goal point is to move towards G. If a path exists between these two nodes, then we have to find the shortest path using this A star algorithm. Now there are two types of weights uh, assigned here. One is in brackets, parenthesis, and one is associated with the edge. Now this edge node, if you remember the equation that we just studied, this edge node is the cost from starting point to the destination point, and this value is the heuristic value of cost of this particular node. So these bracketed values are h of x, and this value is g of x. Now starting point is S, so we have to create, according to the A star algorithm, we have to create two lists. One is the open list and one is the closed list. In the open list, we will add all the destination points of the node that we are exploring. And in the closed list, we will only put those nodes which we have already explored one by one. So we'll always start with the starting node, which is in S in this case. So firstly, we will add S in the open list, and closed list will be empty. Then we will explore S, and as you can see, S has three destination points, A, B, and C, but none of them are our goal. So we will explore S like so, and it has three connections, A, B, and C. Now we will calculate f of x of each node, A, B, and C individually, and update our open list. This left list that you see here is the open list, and the right one is the closed list. As you can see, closed list only contains those nodes which have already been explored. In this case, it is S. So we will calculate the cost of each path starting from this node S. From S to A, we calculate the cost as g of x plus h of x. In this case, 4 plus 8. In this case, it is 12. So we update our priority queue or open list in this way, in such a way that at the top of the list, the node that has the lowest cost possible appears at the top of the list. In this case, S to A is 12, S to B is 16, and S to C is 16 as well. You can go ahead, pause the video, and calculate the distances or costs yourself and verify. So in this case, A is the most promising path as it is the minimum cost path. So we will next explore A in this case according to our priority queue. So A will be part of closed list, and going from S to A and from A we can either go to B or D, as can be seen from the original graph. So from A to B, it makes a total cost of 18, and from A to D makes a total cost of 14. Now how are these costs calculated? Just remember that we have to include the previous edge costs as well. We cannot ignore those costs because our starting point is this, so we have to include the starting point values. So start calculating from S to B, we have 4 plus 8 plus 6. And from S to D, we have 4 plus 5 plus 5. This way we calculate the costs, total costs. Now the next, according to our list, the next promising node is D, which has the lowest cost. So we will explore D next. And as you can see from the graph, we can either go from D to H, I, or F. So we have three paths, H, I, and F. We calculate the costs individually for H, I, and F and add them to the priority queue and update the priority queue accordingly. I hope you all know how to update the priority queue for the incoming values. If not, we can explore. You can explore one of my videos of priority queues, how these are implemented. Now, the next lowest cost path is F, or unexplored. This is also unexplored. So we will add F to the explored list or closed list. And from F, we can go to directly to G, our destination path. So from F to G, we have the destination path, and next we have added or updated our priority queue by adding the G node, which is our destination node. Uh, as you can see that it is our destination point is reached, but the algorithm doesn't stop here. According to the algorithm, G, or our destination point, must be part of closed list in order for the algorithm to terminate. So we will keep on exploring. The next in our list of nodes is B, which is this one, not this one, because this costs 18 and this costs 16. So next we will explore B, and from B we can go to D, only one path. And as you can see that D is already past part of our closed list, so we don't need to go further from there. Next we can explore C. From C we have three paths, D, E, and F. D and F are already explored, so we don't need to add these paths. But E is unexplored, so we'll part of this make E part of this unexplored or open list, which costs around 36. Next in our list is B again, which we have already explored according to this closed list. So we will just remove this top node. And next to B is G, as you can see, which has a cost of 23, and it is also our destination point. So this is where our algorithm stops. And now we have the calculated cost of starting from this S to our destination point G. So constructing path from S to G, the shortest path being S to A to D to F and to G. This is our shortest path that is calculated. Path obviously exists. In this case, it is from S to A to D to F to G. This way you can calculate the shortest path, and you can find the shortest path using A star algorithm. I hope this video helped you in understanding in better understanding of the concepts of how to implement A star algorithm. I'll try to add code associated with this, Python code associated with this, and try to explain it through that code. Until then, Allah Hafiz.